Good day everyone. In this video, I will explain how to solve the question involving the relation f. So in this question, f is defined as the set of all ordered pairs x, y in the real numbers where the second component y is equal to x squared. So our first question is list 5 different ordered pairs that are in the set f. So for part A, we are given that the relation f is defined by y equal to x square. This means that for any x value, the y value must be square of x. So I will choose 5 different x values and calculate their corresponding y values. First, when x is 0, y equal to 0 square, which equals to 0. When x is 1, y equivalent to 1 square, which is equal to 1. When x is 2, y equal to 2 square equivalent to 4. When x is negative 1, y equal to negative 1 square equivalent to 1. When x equals to negative 2, y equal to negative 2 square, which is equal to 4. So, the 5 ordered pairs in the set are 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. So based on the information, we have come up with the 5 ordered pairs. So for question 4b, we need to specify the elements for the following sets A, B, C and D. So for part A, we are told that element x and 4 is in F. Since F is defined by y equal to x square, this means 4 equal to x square. So now we need to solve for x. X equal to plus minus square root 4. And this will give you x equal to plus minus 2. So the set A is element negative 2 and 2. The set A contains element negative 2 and 2. Now we need to repeat the same step for part 2. So for part 2, the given point is x and 10. Again, it must satisfy the equation y equal to x square. So 10 equal to x square. Solving for x, x will give you plus minus square root 10. Therefore, set B is the set whose elements are negative square root 10 and square root 10. Next, for part B, we need to specify the elements for the following sets A, B, C and D. So for part A, we are told that element x and 4 is in F. Since F is defined by y equal to x square, This means that 4 equal to x square. So now solving for x equal to plus minus square root 4, which will result in plus minus 2. So the set A is the set whose elements are negative 2 and 2. For set B, which is part 2, the point given is x and 10. Again, it must satisfy the equation y equal to x square. So 10 equal to x square. Now solving for x equal to plus minus square root 10. Therefore, the set B is the set whose element are negative square root 10 and square root 10. So for part 3, which is set C, the x value is fixed at 5. Since point 5 and y belongs to F, it must follow the rule, which is y equal to x square. So y equal to 5 square, which gives you y equal to 25. So the set C is the set whose element are 25. For part 4, which is for set D, the x value is negative 3. So using the relation, y equal to x square and the given x is negative 3. So just substitute into the equation, which gives you y equal to 9. So the set D is the set whose element is 9. So that's the complete solution for this question. We identified ordered pairs in the relation and determined specific x or y values based on the definition of y equal to x square. Thank you for watching.
Hello, in this video we'll be analyzing 3 relations on the set of integers, and for each of it we'll be determining whether it is reflexive, symmetric or transitive. Before we begin, I'll be stating the definition that we'll be using in this question. So first of all, we need to know the definition of reflexivity. Reflexivity means that A relates to itself. So next we need to know the definition of symmetric. The definition of symmetric is A relates to B and B has to relate to A. Third, we have transitivity, and the definition of transitivity is A relates to B and B relates to C, then A has to relate to C. Now let's move into the question. For our question A, let R be the relation on set of integers where all A, B are elements of the set of integers. A is related to B if and only if A minus B is less than or equal to 2. So we need to find out if the relation R is reflexive, symmetric or transitive, and we also need to justify our answer. So for question A, is relation R is reflexive? We can say yes, because we can prove it using this. Since reflexive means that A relates to itself, A minus A is equals to 0, which is less than equals to 2. Now is relation R in question A is also symmetric? We can say that the relation R is symmetric, and we can prove by assuming that A is equals to 7 and B is equals to 5. Since for symmetric, the definition of symmetric is A related to B and B is related to A, we can prove it by using this method, where A minus B is equals to 7 minus 5, which is equals to 2, less than equals to 2. And when we do it vice versa, where B minus A is equals to 5 minus 7 equals to negative 2, we get a value which is less than equals to 2. So we can say that this relation is symmetric, because if A minus B is less than equals to 2, then we will be also getting that B minus A is also less than equals to 2 for all A, B, which is element of the set of integers. Okay, now let's find out if the relation R is transitive or not. So for transitive, we need to make sure that it satisfies the definition of transitivity, which states that A has to relate to B and B has to relate to C, and A will be relating to C. So as in for transitive, we can say it's no. And how do we prove this statement? Let's just assume that A is equals to 5, B is equals to 3, and C is equals to 1. So when A minus B the value we obtain is less than equals to 2, and we do it B minus C, the value we obtain is still less than equals to 2. So we can state that A is related to B, and at the same time B is also related to C. So this actually satisfies half of our definition of transitivity. But before we state it's transitive or not, we have to make sure that A also relates to C. So to know that A really do relate to C or not, we can prove it using this method, where we can do A minus C, which is equals to 5 minus 1. We get value of 4, which is not less than or equals to 2. So we can clearly see that A does not relate to C, because we are getting a value which is not less than or equal to 2. So we can conclude that the relation R is reflexive and symmetric, but it is not transitive. So since it does not satisfy all these three definitions, which is the reflexivity, symmetric, and transitivity, we can state that relation R is not an equivalence relation. And that's the solution for our question 5A. So let's continue with question 5B. So for question 5B, we have to let R be the relation on set of integers, where all A, B are elements of the set of integers, and A is related to B if and only if A is a multiple of B. So is R reflexive, symmetric, or transitive? And we'll have to justify all our conclusions. So let's start. As for reflexive, you can see that our relation R is reflexive, yes. We can prove it by showing that it actually satisfies this condition where A is multiple of B. If A is multiple of B, then A is equals to constant B. So let's just assume that when A is equals to constant and A, constant multiplied by A, where the constant is equals to 1, we can say that A is equals to 1 times A, and we'll be obtaining A is equals to A for all A which is element of this integer. Since reflexivity means that A relates to itself, so we can clearly see that we do get A again after multiplying with a constant. So this actually satisfies this condition where A is actually a multiple of A, since we are obtaining A after multiplying with the constant K. Okay, now let's just see if our relation R is symmetric or not. So for definition of symmetric, we have to make sure that A relates to B and B relates to A. So for that, we can prove by using this. Let's just assume that A is equals to 12 and B is equals to 3. You can clearly see that 12 is a multiple of 3, but we clearly know that if we have to satisfy the definition of symmetric, B has to relate to A as well. But we can clearly see that 3 is not a multiple of 12 in this case. So we can say that this relation R is not symmetric. Now, as seen for the transitivity, we can state that this relation R is transitive, and we can justify our answer by stating that let B as multiple of C then it will be like B is equals to constant C. When A is equals to K multiplied by constant C, is equals to K multiplied by the constant K and L, C for all A, B, C that are set of the integers. Since the definition of transitivity means that A has to relate to B and B has to relate to C, and at the same time A also has to relate to C, this shows that when we multiply A is equals to K multiplied by B, the constant K is multiplied by B, we will be obtaining the same thing where the B multiplies the C, and this shows that it satisfies the definition of transitivity. So you can say that A is a multiple of C in this case. So as for conclusion, we can conclude that the relation R is reflexive and transitive. But our relation R in this case is not symmetric, since it does not satisfy the definition of symmetric. So since it does not satisfy one of these three definitions, the relation R is definitely not an equivalence relation. Okay, before continuing with question 5c, Let me just restate the definition of reflexivity, symmetry and transitivity so that we can refer to it. Okay, now let's continue with our question 5c. So let R be the relation on set of integers where for all a, b elements of set of integers, a is related to b if and only if a is a factor of b. So in this question C, we need to satisfy this condition where a is a factor of b. So is R reflexive, symmetric or transitive, and we have to justify all our conclusions. So let's start with the question. So we can say that the relation R in our question 5c is reflexive. And we can prove it by stating that if A is a factor of B, then B is equals to now A is a factor of then A is equals to A multiplied with constant. We are doing it like this. This is because to show that if A is factor of B, then B is equals to A multiplied by a certain constant. Now since reflexive, the definition of reflexive means that A relates to itself, we are stating that A is a factor of A, which also means that A will be equal to A multiplying with another constant. Then we can say that A is equals to A, and let's just assume the constant K is equals to 1. We will be getting A is equals to A, which satisfies our definition of reflexive for all elements of A. Now let's check if our relation R is symmetric or not. We can state that our relation R is not symmetric in this question, and we can prove by assuming that let A equals to 1 and B equals to 3. And we can clearly see that if 1 is a factor of 3, then it's obvious that 3 is definitely not a factor of 1. So since it does not satisfy our definition of symmetry, which means that A need to relate to B and vice versa, we can say that this relation R is not symmetric. So as in for transitive, our relation R is transitive, and we can prove it by letting B to be our factor of C. Then we'll be obtaining that C is equals to B multiplied by a constant M. When A is a factor of B, we can state that B is equals to A multiplied by constant K, and C is equals to B multiplied by constant M. Then we can conclude it as C is equals to A multiplied by constant K multiplied by M. Thus, we can clearly see that A is a factor of C, and C is equals to A multiplied by constant K multiplies constant M for all A, B, C, which is elements of the set of integers. So since you can clearly see that A is a factor of C with this equation, we know that a relation R in this question satisfies the definition of transitivity. So to conclude, we know that our relation R is reflexive, and transitive, but it is not symmetric. Relation R is not an equivalence relation. So that's the solution for our question 5C, and that's the end of discussion for our question 5.